Hi everyone, and welcome back to my lecture series on hardware for deep learning. Now we continue part 4, reducing the complexity. So after we discussed the lightweight models, now let's move on to reducing precision. Okay, so before we start, we've got to discuss a little bit of the taxonomy. So precision refers to the number of levels. The number of bits is log 2 of the numbers of levels we need to represent. Normal precision is floating point 32 or FP32. So we see over here on the right side, we have the sign bit, which is a minus or a plus, 0 or 1. We have the mantissa bit, which is 23 bits, which shows us the precision after the dot, so it's minus 1 dot something. And the exponent is 8 bits of what the exponent of the over here is. Okay, so if we want to represent minus 1.112934 times 10 to the minus 16, it would be with this bit representation. Okay, that's normal precision. Low precision is is fewer bits, so it's either floating point 16 or even integer 8 or fixed point with 8 bits. So for example, a fixed point 8 bit of 12.75, it has the sign bit, that's 1 bit, and then it gives 4 bits for integer and 3 bits for the fractional, where the point is fixed over here. So we treat this basically as an integer because the point, the decimal point is always at the same place. This is 12.75 in an integer 8 representation. Mixed precision is utilizing several precisions like FP32 and FP16 in the model, and we'll discuss that a bit later. And quantization is mapping data to a smaller set of levels. So we have linear, for example, which is fixed point, like an int 8 or a binary type of a quantization, or a nonlinear quantization where we compute the quantization, which could be either with floating point or, for example, with a log domain, or we could use a table lookup such as a learned quantization, and we'll discuss those in a bit. Okay, number representations. So here we have a bunch of number representations. FP32, as we showed before, it has a sign bit, it has 8 exponent bits, 23 mantissa bits, provides us a range from 10 to the minus 38 to 10 to the 38, and it has this very high accuracy. If we go down to a 16-bit representation with floating point 16, we again have a sign bit. We have fewer exponent bits, so only 5 exponent bits, and fewer mantissa bits, only 10, and we get a total of 6 times 10 to the minus 5 to 6 times 10 to the 4, and it's a much worse accuracy, so our accuracy is only 0.05%. If we go over to an integer 32 representation, we have a sign bit, and all the rest are the mantissa or whatever the integer, and so that gives us 0 to 2 to the 10 to the power of 9, and the accuracy is a half. And when we go down to integer to 16, we have 15 bits for the integer part, and into 8, we have 7 bits for the integer part. Of course, with fixed point, we decide where we want the point in the middle here. Because we can use a reduced representation, Google offered something called the bfloat16, or the brain floating point format, and that's just a different partitioning of the exponent versus the mantissa in a 16-bit floating point representation. So we have the sign, we have 8 bits of exponents and 7 bits of mantissa. What that does, basically, it lowers the accuracy quite a bit because the mantissa is much shorter, but it keeps a large dynamic range. So the dynamic range is pretty much e to the minus 38 to e to the 38, very similar to our floating point 32. So we keep the similar dynamic range. Makes it easier for training and debugging than a standard FP16, and this is already supported in Google TPUs, Intel Xeons, Nirvana, and other processors, other AI accelerators, and it's commonly used because often the floating point dynamic range is more important than the accuracy for training neural networks. There is also dynamic fixed point, where we basically don't keep the same fixed point representation in all layers or in all parts of the calculation. So we may decide that here we're going to put the floating point over here, where we give 5 bits for the mantissa and 2 bits 5 bits before the decimal point and 2 bits after, and maybe at another point we're going to even keep those all 7 bits even shifted to the left and keep all this integer and have no fraction. So this is a kind of a thing that you can do, use different ranges for activations, biases, weights, gradients, and different layers. And this is all due to the cost of operation. So in ISSCC 2014, Mark Horowitz of Stanford showed this this graph that we actually showed a bit earlier on, at least part of it, and we see that the adds are much cheaper than multiplications, and everything is much cheaper than memory access. But also within them themselves, when we use an 8-bit versus 16-bit versus a 32-bit AND, we have an order of magnitude change in the amount of power it costs, and we have something like that in the amount of area it costs to make the adder. If we go over to a floating point matter, we're already quadrupling that, and for a 32-bit floating point adder, it's even about 9 times as much as a 32-bit standard add, and we also have another order of magnitude, or even more than that, in area. When we go over to multiplication, so multiplications are much more expensive than additions, and even in integer, they cost quite a bit more, especially when we move from an 8-bit to 32-bit. And if we move from a 32-bit integer to a 32-bit floating point, we also get an increase. It's not as substantial, but it's still quite a bit. Okay. However, even an SRAM read on chip is much more expensive than any of these additions or multiplications. And when we go off to DRAM, we get another 2 orders of magnitude increase in energy. So that's why we have this motivation to reduce our precision, and also as a side benefit for reducing the precision and having cheaper calculation and cheaper hardware, we also need less storage, so we need to do less off-chip memory accesses. So one of the ways that is very commonly found today is mixed precision. And mixed precision refers to using both full and reduced precision in a model. So we're going to identify the steps that require FP32, normal precision, and use lower precision such as FP16 everywhere else. And this has been shown to provide a 2 to 4x speed up. So you see different popular networks and the different types of speed ups that were found if they use this mixed precision, where some of the places we used 32 bits and some of the places we lowered it to FP16. In fact, industry has come up with inference to be at an 8-bit integer precision, and for training, Google TPUs now support a mix of FP32 and bfloat16. NVIDIA Tensor Cores accelerate FP16 matrix multiplications and convolutions. Okay, so as you can see here from NVIDIA, we can have these matrices that are in FP16, and they may have the accumulation in FP32 or something to keep better precision over there. And Keras provides a mixed precision API in TensorFlow. So mixed precision has become quite popular. Quantization is a further level of this, where we're, instead of just changing the precision, we're actually mapping to a smaller set of levels. So floating point, which is trying to actually represent real numbers, is mapped to like integer, like an int8, which is a quantized level, much highly reduced a number of levels of representation. How is it done? It's actually quite straightforward. So what we want to do here is, if we look at the graph over here, we have our floating point, which is supposed to represent, let's say, a minimum of minus 1.00 and a maximum of 1.00, and there's a large number of values in the middle, almost continuous. We would say it's trying to represent this integer, this real number. However, in the integer, we only have 256 values for an int8. So what we're going to do is we're just going to draw a line between the minimum integer level and the minimum real level to the maximum integer level and the maximum floating point level. We're just going to put a straight line between, and then each integer level here will represent its representative floating point level down here below. That's this simple equation here. So the quantized value we're going to get is the floating point value divided by some scale factor. That's basically the slope of this plot here, plus an offset, which is basically where this plot crosses the 0 point on the x-axis. Okay, so how are we going to figure out this scaling factor? The scaling factor is basically the slope of this, so it's the maximum of the floating point minus the minimum of the floating point divided by the maximum of the quantized level divided by the minimum of the quantized level. And while the maximum and minimum of the quantized level is in a way given, that's not true for the floating point level. And the floating point level, we have to look at our data set, and it might be very large. And the farther out we take this minimum and maximum, the the more shallow the slope is going to be, which means that each integer level is going to be representing a lot more numbers on in the floating point space. So what we want to do actually is we want to tighten up the distribution and have our maximum and minimum floating point levels as close together as possible. So if we have some sort of normal distribution with some outliers, because that way we'll have more values of integers that will be kind of distributed around where we have most of the integer values will be distributed around where we have a close floating point representation. And luckily, actually, a lot of the neural networks have this type of distribution, so we can kind of clip at some points over like here and here our minimum and maximum floating point level, and say we take any outliers here to be the minimum and maximum value, but we have all our 254, say, integer 8 levels that are left representing the numbers over here. So it gives us a tight distribution around where most of our real values actually sit. So quantization has actually a lot of tips and tricks, and you have to actually play around with it a lot and try different things to get it very well. But in general, when we use uniform quantization, which is what I showed you on the previous slide, it's pretty straightforward. Taking floating point, turning into integer, and with, as we saw with an add, we get 30 times less energy, 116 times less area than a 32-bit floating point. For a multiply, we get 18.x times less energy, 27.5x less area than a floating point 32 representation, and that's really good. However, we have to notice that, for example, in a Mac, the fact that we quantize doesn't mean we can stay everywhere with this low bit representation. So if we have n bit weights in input, so we need an n by n multiplier, as you can see here. This is an n bit multiplier. This is an n bit multiplier. The output is 2 to the n bits, but the accumulator has to actually have 2 to the n plus 1 bits, where m is log 2 of c times s times r. So we actually have a much larger representation in here internally inside the Mac, but we can usually take the answer and then quantize it back down, because we're going to go to the next level, which is again going to get an n-bit input. Okay, so this has been shown not to have a very significant input on accuracy if the distribution of weights and activations is centered near 0, and 8-bit arithmetic, as I mentioned before, can be used in Google's TPUs, NVIDIA's Pascal, Intel's NNPL, and other platforms. It's actually very common to use 8-bit integer quantization for inference in commercial products. So one of the things here with this mixed precision is that we may be using at different layers, different widths of our inputs and our weights and so forth. So we might want to have configurable max. And there have been several works about this. In fact, the source over here from JetCast actually provides a large review of this. So you have, for example, just data gating the max so you don't waste power when you're not using a part of it. So if we have here an 8-bit multiplier, and then we want to reduce, and at some point we want to only do a 4-bit multiplication, we can just gate off all of this part of the multiplier, and then at least it doesn't waste power. Or maybe even we can do an 8-bit by 2-bit and gate all of this. This type of an approach, it will save us power, but it won't save us any area or give us speed benefits or anything like that. So there are other different things that can be done, and one of them is even to go to the extreme where we have a bit serial design where we actually use some sort of a bitwise calculation, kind of like an add and shift to do this, and then just by changing the number of clock cycles each calculation takes, we can play with the precision. So it's a trade-off of latency versus area and probably power. So there have been many of these approaches, but all of them have overhead, and sometimes this overhead reduces the benefits that you get. So that was discussing the reduced precision, and now I'd like to go over to aggressive quantization, more aggressive things than what were shown before. So what we discussed before was uniform quantization. And in uniform quantization, the values are equally spaced out. So we had this distribution that was something like this, let's say with our weights, but we decided to take our integers and divide each quantized value to have some sort of space of this. So we have very few values that are they get this integer value, while this represents a lot of values that we don't exactly like that. So quantization, the better fits the distribution, we can achieve better accuracy. And one example of that is log domain quantization. So with 4-bit log domain quantization, VGG16 shows only a 5% loss versus 28% with uniform quantization. And this is actually shown here. So here with log domain quantization, we have a lot of values here around where our weights are tightly distributed, whereas we have much fewer values over at the areas where we have fewer weights. Not only that, with log domain quantization, we can replace multiplication with bit shift, and that's also a very good thing. There's another thing that is called weight sharing, for example, through learned quantization, and that can provide an even better solution. So let's see how we do this learned or trained quantization according to the methodology that Song-Han presented in his PhD work. So we have all these different values here: 2.09, 2.12, 1.92, 1.87, and what we say is let's get rid of them, and instead of that, you just use something that's some sort of centroid of them. So we use 2.0 to represent all those, so all these weights share the same quantized value. And it works according to the pipeline that we see over here. We first cluster the weights, then we generate a code block, we quantize the weights with the code block and retrain the code book, excuse me. Going from 32-bit down to 4-bit, we get an 8x smaller memory footprint, and we can keep very good accuracy doing this. So how does it work? How does this trained quantization work? So over here on the left, we have our matrices. These are our weights. We get all these values that are 32-bit floating point, and we have the gradients from this round of training, and we see that they're also in 32-bit floating point. So the first thing that we're going to do is we're going to cluster the weights. So using a k-means clustering, we can say, well, we're going to do it in the example here to 2 bits. So we have 4 values, and everything that's blue over here are close together, everything that's green are close together, and so forth. And we're just going to give them in a code book a name. The green ones are going to be called 0, the yellow one, the orangish ones are going to be called 1, the reddish ones are going to be called 2, and the blue ones are going to be called 3. Okay, so we did that clustering, and now we're going to find a centroid for each and every cluster. So we take the blue colors, we add them all together, divide them by 4, and we get 2.0. We do the same thing, and we made the numbers really nice here. So the clustering brings these nice numbers: 1.5 for the red for index number 2, 0 for index number 1, and -1 for index 0. Okay, so once we did that, now we're going to take these each of these codes, each of these groups, and so we have like the blue group, which is these 4, and we look at their gradients, and we're going to mark those. So we took these 4 gradients, and we're going to group them together over here. So each of these gradients that belong to this blue group, they're going to be over here, and we're going to do the same thing for all the other groups. So each of these groups, we take their gradients and we group them together. Okay, now what we're going to do basically is we're going to do reduce, which means we just add these gradients together, and we get for the blue group, the reduced gradient is 0.04, for the red group it's 0.02, for the yellow group 0.04, and for the green group it's -0.03. Now doing that, having our centroid that we found over here before, and having our reduced gradient over here, what we're going to do is we're just going to add those together. Of course, we can apply a learning rate to the learned reduction, and then we subtract the learned or the reduced times learning rate gradients from the centroids that we found, and these are basically updated weights that we have. So now instead of all of these blue ones, we're going to use the value 1.96. Instead of these red ones, we're going to use 1.48, etc. Okay, so as we see, what we did here is these were our original values in our matrix, and this was the distribution of the weights that were learned. What we're going to do after quantization, and here in the graph here, we actually are doing it on a 16-bit quantization and not a 16-value quantization, a 4-bit quantization, not a 2-bit quantization as we showed in the example. But for the example, so all the blue ones were represented by our learned weight here, right, and all our red ones by this learned weight, and etc. And finally, we get the quantized value, the 16 quantized values, and the distribution is shown here. So that's a train quantization, and 8-bit quantization on convolutional layers and 5-bit quantization on fully connected layers was achieved no loss of accuracy on AlexNet. And when we used an even more aggressive quantization with 4-bit on convolutional layers and 2-bit on fully connected layers, we arrived at only 2% loss of accuracy, which is really nice, and it's a huge savings in power, area, etc. Okay. However, we do need a cookbook for index translation, and later on in the lecture, we'll discuss deep compression and show how that cookbook was done. So that was a nice, very aggressive train quantization, but there's even more aggressive quantization that can be shown. So one of the first approaches was ternary connect, and there's a lot of work that's been done on ternary quantization, and you can see kind of why. So if you have some sort of a normal distribution, we can go and we can say that we'll divide the areas into 3 values: the value on the left, the value in the middle, and the value on the right. We train with real valued weights. We ternarize the weights to the set that includes 0 and some sort of positive and negative weighted factor. So it's not necessarily -1 and 1. It can be -h and h. Okay, so that's ternary connect, and there have been different results that have been shown on different data sets. Binary connect was a more aggressive even approach to that, and this was by the guys at Montreal, where they used binary weights. In other words, -1 and 1. 0 represents -1 and 1 represents 1. However, they kept the activations in full precision. It makes the multipliers very simple. You just have to look at the sign bit. Quantization is also really simple. You just look at the sign bit, and that's the quantized value. Accumulation was still done at full precision. In the paper of Binary Connect, they presented the math and the approach to do backprop with this. It actually, backprop uses real valued weights that is clipped at -1 and 1, and the methodology that they use has been applied in the even more aggressive approaches, such as binary net, binarized neural networks, XNOR net, and other ones that binarize both the weights and the activation. So now everything is basically -1 or 1. Having -1 or 1, as you can see here, what we do is we take our activation, and what we do is we quantize it to a 1 or to a 0. A 1 or to a -1, which is represented by a 0. And then we have our weights that are also 1 and -1. We do this times this, this times this, this times this, and we add the 3 of them. But this multiplication, the difference between it and multiplication that we did in something like an integer or a floating point, is that all we need for a multiplier is actually an XNOR operation, which can be shown here. So each of these multiplies is just an XNOR operation, one single gate. Finally, all we have to do is actually count how many 1s versus 0s there are, and that's what's called pop count or population count, and that's another type of a digital block that we can implement. Okay, usually in most of these networks, the first and last layers were kept at full precision. That helped it get to nice accuracy, but still, this is a very, very aggressive reduction. It allows things like in-memory computing, and it's pretty popular to be used. So just as a summary from Vivian Z's tutorial, you can see different ways of reducing precision and aggressive quantization, starting from like a nonlinear quantization like lognet or weight sharing, which I showed you before, dynamic fixed point, weight reduction with ternary weights, binary connect, and binary weights and activation, such as binary neural nets and XNOR net, and the different accuracy loss and etc. that we get from them. Okay, the final subject that I want to discuss with you is pruning and the method called deep compression that was presented by Song Han. So just as a precursor to this, I want to note something called dropout, which I haven't discussed in this lecture before. So a well-known technique for eliminating overfitting is called dropout. It's something that used to be used often. During each iteration of training, we zero out a random fraction of nodes in fully connected layers, and then during inference, we use all of the connections. So basically, we have all of these fully connected layers, and we randomly decide a certain percentage of them just to eliminate them by zeroing them out, and then go through an inference, backprop and so forth, but then we reconnect them and choose other ones to drop out and so forth. We keep doing this over and over again, and it helps eliminate overfitting of the data. However, this is just done during training, and when we go and do our inference, we actually use or when we deploy our model, we use all of the connections that were learned. This is, again, for overfitting and regularization, but batch normalization has almost made this unnecessary, so it's not popular anymore. However, it raised the question, do we actually need all the synapses in our networks? And if we look at biology, it seems that all humans, in fact, all mammals, we prune synapses. So axons and dendrites completely decay and die off during our lifetime. It starts near birth and continues into the mid-20s. So you can see that we're born with about, or when we're newborns, we have about 50 trillion synapses. It grows to about 1,000 trillion synapses at the age of 1. But when we grow up, it reduces to about 500 trillion synapses. So this is something that is actually common in the human body as well. And the first work, or the seminal work about this, was called Optimal Brain Damage by Jan LeCun, all the way back in 1989, where he suggested pruning neural networks, computed the impact of each weight on the training loss, called this weight saliency, and removed the low saliency weights and fine-tuned the remaining weights. Okay. However, this is not Dropout. In Dropout, what we did is we pruned the synapses during training. We removed the synapses during training, and we replaced them during inference. But in pruning, we actually remove the synapses for good. So before pruning, we have this fully connected network, and after pruning, we got rid of all those connections, and we deploy a much smaller model, actually. So this is called pruning of deep neural networks, and it leads to sparsity, and sparsity is really good. If we have sparse matrices, they're easier to compress. We can skip multiplications by 0. We may be able to store less stuff in our DRAM and so forth. And in Songhan's work, he showed that 90% of the connections in AlexNet can be pruned without incurring any accuracy loss. In other words, we have these networks that have way too much information in them, and we can get rid of 1 out of every 10 synapses in there. That's really amazing. The way he did it is he took a threshold, and anything that was under a certain threshold he got rid of. Okay, so he used this train, prune, retrain pipeline. So we train the connectivity, prune connections, and then retrain the weights. And from 60 million connections in AlexNet, he was able to reduce it to 6 million connections. So let's see how it works. So at the beginning, we train the connectivities. We don't have any parameters that were pruned away, and we get a 0% accuracy loss versus our baseline. So this dotted line here is our baseline. Then as we start pruning away our parameters, we see that we lose accuracy on the y-axis. Okay, so after we've removed a lot of these parameters, what we can do is we can retrain. And retraining, you see what it does. It improves, again, our accuracy, and we can continue iterating over this until we get to the point where we have no loss and we get 90% of our weights were pruned. So you can see also the effect of pruning. On the convolutional layers, we were able to get a 3x reduction in the size. Fully connected layers, it's really aggressive, and we can get a 10x reduction in the size of the fully connected layers. So fully connected layers seem to have really way too much information. I guess that's why convolutional layers are actually so successful. Another thing that's interesting is that pruning changes the weight distribution. So before pruning, we saw that the weights are kind of distributed in around 0 like this. When we prune them, we don't have any of this middle area. We get rid of everything under a threshold. So we have these two like spikes in the areas of the weights because we got rid of everything in the middle that was really close to 0. And then when we retrain it, also it distributes kind of around these areas again. So we should consider some hardware efficiency things when we're doing pruning, because pruning leads to irregularity, and this is really difficult to parallelize in hardware. So what we can do is on the one hand, we can do load balancing during pruning. So we can sort the weights in every submatrix and prune the same amount in each, such that each processing element works on the same number of non-zero weights. However, we still need to index every non-zero weight, and that's kind of hard. Another thing that we can do is actually structurally prune. So we can take a larger thing, not just prune every single value or every single pixel that's possible, but we can prune by row, columns, kernels, or even whole filters. And that way, one index can point to a large space that we got rid of. For example, we can prune a column according to the L2 norm. So as we see here, there's this kind of continuum of how to prune. We can either do a completely irregular pruning, where we have to say everything that was pruned away, we have to keep its hold its index and so forth, or we can prune away whole rows or columns, and then we represent with one index several weights, or we can do whole kernels inside a filter, or we can even do whole filters for the pruning. And that leads us basically to the deep compression pipeline. So deep compression combines pruning, train quantization, and variable length coding in a pipeline, and this was Songhan's big proposal. So we start with an original model. We prune the model by the train, prune, retrain pipeline. Then we quantize according to our train quantization, creating this code book, and then we actually have to do some variable length coding to compress the data itself. So we've discussed this part and this part. Now we'll discuss some of the variable length coding. So how do we store the metadata? Basically, as we said, we need to store an index and a weight for every non-zero weight. Okay, that can be kind of expensive, so we want to do some sort of compression or some sort of smart way to save these. So instead of the actual index, what we're going to do is we're going to store the distance from the previous non-zero index. We'll select a small bit width for the index representation, and if the span is larger, then we'll pad with 0. So let's see how it works here. Okay, so we go to our first non-zero weight, which is over here, and it's actually its memory position is 1, and the distance from the last point is 1 because it's the first one. Okay, and this is its value, 3.4. We're going to use a 4-bit representation for the distance, so the maximum we can go is 16 points away. But the next non-zero value is here at number 5. So what we're going to store is not index 5. We're going to store the distance from the last non-zero index. So the distance to the last one is 4. Okay, and then and this is our value. The next weight is pretty far away. It's at 24. That's the next non-zero weight. And 24 minus 5 is 21. That's larger than 16, which is our largest span. So what we do is at our largest span, which is 16, okay, we're going to say we have a non-zero weight here. It's 16 away from the previous one. However, we're going to put 0 here. And we pruned away all the zeros, so there's no reason to store 0. So once we find a 0, we know that it was just a padded thing to say that our next weight, non-zero weight, is farther than 16 away. So now at this non-zero weight, we only have to have a distance of 3. Anyway, with 4 bits now in the index, we can actually index everything. Instead of having to have log 2 of the whole memory space, we only need a 4-bit index to say the distance from our previous non-zero. Okay, and we use a separate cookbook like this for each layer. Then we use variable length coding, which the idea is that infrequent weights use more bits to represent, and frequent weights we should use less bits to represent. So if we have these guys, they should use fewer bits to represent, and these guys can use more bits to represent because there are very few usages of them. And then something like Huffman coding can be used, and Huffman coding really exploits this thing to heavily compress the data. So that's the Huffman encoding encodes the weights and encodes the indexes, and we're able to even farther compress our data. So here again is the original network that goes through the pruning, gets a 9 to 13x reduction, then it goes to quantization, keeps the same accuracy but with a 27 to 31x reduction, and through the coding it actually arrives at a 35 to 49x reduction through this pipeline, and that's why it's called deep compression. Just as one of the results that Songhan showed, so you can take different nets starting from LeNet down to GoogleNet or ResNet or VGG, and you can see that the compression ratios can be 40% or more, and you can maintain a similar accuracy. In some cases, they even get a better accuracy than the original. One last point that Vivian Z's group did is energy-aware pruning. So the value of the weights alone is not a good metric for energy. Instead of just pruning according to the value of the weights, we can prune according to energy. So let's sort the layers based on the energy and prune the layer that consume the most energy first. And energy-aware pruning that was done by her group, it was able to reduce the ALEKS net energy by 3.7x and outperform the previous works that use magnitude-based pruning by 1.7x. So that's a completely other approach. Okay, so in this lecture, we discussed how to reduce the complexity, and this was based on various talks. Here's Song Han and Vivian Z. These are the two main people who provided the background information for this, and I seriously encourage you to go and look at their lectures, both online or read their papers and so forth.